Okay, our next presenter is Heye Huang from Tsinghua University. And Heye will be talking about an integrated architecture for intelligent evaluation of automated vehicles. Huang was a undergraduate and bachelor student in traffic and transportation engineering in the Central South University, China, where this conference is now physically located in. That's good. Now, Heye is a PhD student at Tsinghua University, and her research interests include connected and automated vehicle risk perceptions and traffic safety, in particularly in the area of decision making, situation awareness, and prediction. So without further ado, so let's welcome Heye Huang for her presentation. So I'm going to make her, give me a second, I'm going to spotlight her so that we can. Over to you, Heye. You can start your presentation now.
Okay, thank you for your kind introduction. Good afternoon, everyone. I'm Heye Huang from Tsinghua University. My lab is focused on the intelligent and connected vehicles. So I'm so glad to give a presentation about an integrated architecture for intelligence evaluation of automated vehicles. There will be 3 parts that I introduce today. Let's start with our research background. With the intelligence revolution, vehicles gradually transformed from manual driving to driver assistance and then to high-level autonomous vehicles, which greatly promotes the reform of vehicle intelligence. Meanwhile, the development of network also supports automated vehicles to achieve driving safety. Automated vehicles has become an important way to create intelligent and safe travel life. However, the frequent accidents of automated vehicles presents a number of safety challenges. Therefore, automated vehicles should pass effective standard tests to verify whether they reach the level of service for people and to truly improve people's trust in them. As we know, automated vehicles have the perception, decision, control, and other abilities, but the challenges is that how to judge the AVs can adapt to various road conditions, especially in complex traffic environments, to ensure the safety and efficiency of driving. And moreover, how to quantify the intelligence level of different AVs. The existing automated vehicle testing and evaluation projects have been gradually carried out, including establishing the automated vehicle test ground and reaching the test evaluation method of the automated system. In this study, we provide a comprehensive evaluation framework like this to achieve complete and accurate intelligence evaluation. In the environmental perception layer, we can evaluate the equipment with the environmental perception function. In the behavioral decision-making layer, the evaluation of behavioral decision-making includes the ability to make reasonable driving behaviors and complex and changeable traffic scenarios. In the motion planning layer, the motion planning layer mainly focuses on how to carry out the velocity planning and the local path planning on the driving process. So we can test the ability to generate a safe and feasible driver trajectory. Through these layers, the evaluation of these functions in each layer can be output through sensors and actors of automated vehicles. Then we will consider how to establish the test platform and indexes. A test environment can be provided for automated vehicles by building a closed test field and restoring a real driving scenario. The test scenario is suggested to cover dangerous scenarios, accident scenarios, naturalistic driving scenarios, and etc. Further, the environment needs to simulate and restore the real traffic scenarios, include the red light equipment, traffic signs, street lights, and other obstacle vehicles, their use, etc. An example of the enclosed test field provided with my article is shown like this. Also, a feasible example of intelligent test platform vehicle is often equipped with some high accuracy sensors, including the IMU embedded system and the microcontrol units, maybe like GPS, back forward radar like this. And the intelligence of automated vehicle is evaluated according to the output of the task through the established intelligence level standard. In the comprehensive road environment, due to the complex and changeable driving scenario, the unpredictable behavior of traffic participants and the improvement of people's requirements on the comprehensive driving process, the reasonable definition of intelligence index needs to be comprehensive, systematic, and quantifiable. So we need to consider all of these requirements to output and develop an evaluation index. So the high-level automated vehicles can generally guarantee the safety, efficiency, comfort, and reasonable behavior in the driving process. Therefore, comprehensive intelligence evaluation index also needs to consider the several aspects like safety, efficiency, rationality, and comfort. Since the intelligence evaluation of automated vehicles is a cumulative process, we need to analyze the energy like this required by the automated vehicles in the pursuit of these performance indexes from the perspective of energy. Since the indexes also interact with each other, so maybe in this index, it will reflect the interaction like a social force between different road users. They will consider uniformly from the incentive of seeking profit and avoiding loss in the driving process. In the proposed evaluation framework, we first set the evaluation indexes of automated vehicles in the whole driving process, then calculate the defined action amount of the whole test process. Finally, the intelligence index is defined to quantify the performance of the test automated vehicles. So the input and output can be outlined. To verify the effectiveness and reliability of the intelligence degree algorithm, we need to analyze two main kind of scenarios. The first one is the scenarios in which the intelligent vehicle changes its lines and on the highway under the normal driving conditions. The second type is the scenarios with high risk, which is maybe near crash or crash. So non-changing scenarios of normal driving is one of the most common scenarios in the driving process. Therefore, we will first verify the index in these scenarios. We first analyze a general open source Heye dataset. Maybe it's just like the legislation dataset, but it could be different because it includes all vehicle locations, speeds, vehicle types, and sizes. The large amount of data, clear location, and speed information are well suited as the inputs to verify the intelligence index. This scenario we extracted is a scenario of 4 vehicles on 2 or 3 lines. It includes like 14,000 frames in Heye datasets. We extracted 179 trajectories. That means the requirements, especially in the land changing process. So we extracted these trajectories. Through these trajectories, we just got the central line fitted by these trajectories. We took this central line as a reference line in the same land changing scenario. So then we let the intelligent vehicle track this driving path according to the real-time surrounding vehicle information. And it can be seen that from the right figure, when the thick blue reference center line is intelligent enough and means the driving requirements of a large number of drivers, the planned rate, the trajectory of the automated vehicle can be highly fitted to the trajectory of a large amount of drivers like this. Similarly, we also designed a large 2 test scenarios considering the safety and smoothness of defined scenario trajectories. Actually, results show that maybe the planned rate trajectory of the autonomous vehicles can effectively avoid obstacles considering the safety influence, and the speed changes of the planned trajectory are gentle, so the smoothness can be satisfied. We then adopt the MIT open source near crash dataset, which contains like 253 videos with high risk or near the collision. Specifically, these videos include all kinds of factors affecting road safety, such as different types of road environments. The whole experimental manipulation of the near crash was tested by 39 participants with driver licenses. So let's look at the details. In driver's hazard detection or hazard evasion task, there are some stimulus sequences. Each trial began with a 250 milliseconds pre-stimulus mask, followed by the video clip and the participants' response, like pedals in the hazard detection condition, well in the hazard evasion condition. Specifically, as shown in these figures, we extract these scenarios. These scenarios include all kinds of factors affecting road safety, such as different types of road environments. For example, the city street, highway, rural roads, and the type of different weather conditions and obstacles. We then classify these videos according to the dangerous scenario morphology and employ simulation toolbox in MATLAB to reconstruct the near crash scenario according to the 12 extracted scenarios. For example, there are 41 cases of sudden swerve, 49 cases of sudden cut-in, and 86. Just as shown in this list. And according to the experimental manipulation of the near-cross stimulation scenarios by 39 participants with diagnosis, we can obtain some interesting results. So there are some behavioral characteristics of drivers in the process of encountering high-risk scenarios, including their interest time, exploring time, critical time to accidents. So their action time and resolution time differences. The time range of drivers' interest in risky scenarios is around 0.3 to 0.6. This experiment videos can be viewed from this above link. Yeah. And the internet, we can see the driver's reaction time and the deviation when taking different controls such as braking, turning right, turning left. The red bar, yeah, in this figure, describes the actual response when the driver encounters critical scenarios, while the gray bar represents the deviation between the actual operation and the ideal response. And this, in the right figure, we compare the effectiveness of our algorithm and the traditional risk assessment algorithm TDC, and about the driver's response. By taking these 3 countermeasures of braking, turning right, left, and turning left and turning right, the ultimate effect of avoiding risks can be achieved. However, there are some differences in the implementation effects of these methods due to different risk perception thresholds of drivers, TDC, and our algorithm in different scenarios. So TDC mainly work based in the need of urgent brake scenario. The main reason is that this algorithm focuses on the latitude of obstacle avoidance, and the drivers identify the most accurate in the process of right manipulation. Possibly reason is that the risk coefficient of right measures is smaller than that of brake scenario, and the controlled space is larger. However, the algorithm we proposed can effectively reduce risks by taking appropriate measures in different scenarios. So, I'm sorry. And in order to test the evaluation methods in different scenarios and then optimize the parameters so as to make it more universal, we investigated the naturalistic driver dataset in more scenarios, including the dataset IND and ROND. This dataset have obvious characteristics and multiple types of road users, which can better verify the actual evaluation effects of our intelligence evaluation algorithms and complex interaction scenarios. For example, we just extract the highly interactive intersections and then draw road users' trajectories and real-time location information. Complex interaction scenarios maybe can be used as the input to the evaluation method to test the intelligence of AVs. So as you can see from this demo, we select a typical urban road sections. Different intelligence levels of intelligent vehicles will lead to inconsistent driving strategies with different risks. So maybe the darker the color, the higher the risk degrees, and the faster the speed, the larger the influence scope. So finally, we will make a brief summary. To conclude, we proposed a practical method to quantitatively evaluate the intelligence level AVs. Besides, we define and verify the symmetric evaluation index by employing the principle of least action. And this experimental results show that the proposed framework can effectively quantitate intelligence and evaluate the performance of automated vehicles, maybe like under various scenarios. Oh, okay, thank you for listening.
Thank you, Huang, for the nice presentation. So I know that health-wise is probably not a very good day for you today, but thank you for doing the presentation.
Okay, so, my pleasure.
So we have just received one quick question. Probably will be will not go further beyond one question, considering your health and the time. So one question that have been come from Farouk Break saying that his questions about the comprehensiveness index on slide number 13. Now, how to calculate the weight? Yes, slide number 13. And his question is how to calculate the weight for 4 components.
Actually, in this, in the determination of evaluation index, we need to know the whole process of driving autonomous vehicle. Because if you want to test a vehicle, how intelligent it will, you need to know you need to evaluate from its performance. So we choose the principle of least action to describe the whole process of vehicle driving. And finally, we just consider the indexes, including safety, efficiency, to combine and output a comprehensive indexes, which can describe the ability that a highly intelligent vehicle needs to have. And through this normalized output, we can define the level of different intelligent vehicles, because we can calculate one S. This S maybe it's just calculated by theory, so it's the minimized S function, and we then calculate the actual S. So we will compare and normalize the difference between actual S and the ideal S. So to output the different intelligence of a vehicle.
Okay, thank you, Heye. And by the time you have been talking, we have received another question from Tommy. And his question was, how do you choose the high risk scenarios and based on what indicators?
Okay. With understanding, maybe his question is about this scenarios, so I extracted, right?
Yes.
Actually, this is
based on what indicators you have selected those high risk scenarios. That's the question.
Yeah, actually, because we know that if you want to test vehicle's ability, you should not only maybe test it in just normal driving, but in high risk scenarios. You should know how it will adapt to different high risk scenarios. So we divided and extracted scenarios from the MIT open source data set. These scenarios are just maybe connected by MIT 8-9. So I just divided this into according to these videos and reconstructed in MATLAB I reconstruct the scenarios in MATLAB to simulate the same scenario and the same parameters. Finally, we can use these scenarios to like obtain or as the test benchmark to test the driver's response, how the driver will respond in these scenarios and how our algorithm responds. Yeah.
Okay, thank you. That's very interesting. So thank you for your presentation today. I think that we'll go to the next presentation now. You can stop sharing and turn off your video. It will be good.
Okay.
Thank you, Heye.
Thank you.